Okay.
So you want interruptions while you speak?
Yes, I do. That's part of why I'm recording is to get feedback from this audience. Okay, so today I'm going to tell you about ongoing work to turn JavaScript into a decent distributed secure programming language, and to demonstrate that we've gotten decent abstractions. For doing so, I'm going to take on a hard problem, two-phase commit distributed escrow exchange among mutually suspicious parties. And in the process, also explain the equivalence we found between secure distributed escrow exchange and two-phase commit among mutually suspicious parties or strangers. Next. The variant of JavaScript we'll be using is what we call Dr. SES, which is Distributed Resilient Secure ECMAScript. It's secure by building on the SES library, which is a library that runs on ECMAScript 5 and restricts JavaScript to the object capability subset of JavaScript. It restricts further JavaScript programs, the object capability subset. And the essence of object capabilities is that one grants authority by transferring unforgeable references, by sending them messages. It's distributed by building on the Q asynchronous distributed promise library. And the way in which it's distributed and secure is that the Q library stretches the reference graph cryptographically among machines, substituting unguessability for unforgeability. And it's resilient by building on the Ken system of distributed orthogonal persistence. And here's where we get hypothetical, which is that Ken does not yet exist for JavaScript. It's been implemented for Java, Scala, and C, but not yet for JavaScript. The emphasis on today's talk will be on the distributed part. For the secure part, previous talks of mine that are available on the web deal with those in detail. Okay. Q adds three important primitives to JavaScript, which are...
Do you mind mentioning what page number you switched to when you switched?
Oh, I'm sorry. Next, Q primitives.
Just so I don't get out of sync. You're on page 3, right?
I don't have the page numbers in this presentation mode. It's the first slide titled Q primitives.
Okay, thank you.
Okay. So Q adds three important primitives to JavaScript, what we call the eventual send, the when catch expression, and the Q.defer expression that makes a fresh promise resolver pair. Next, the slide labeled immediate call. So before explaining the eventual send, let's review the familiar immediate call. Let's say that Alice, Bob, Carol, and Dave are four objects which are local to each other. They're in the same address space on the same machine. Next. And Alice does the familiar bob.foo of Carol. We say that Alice is synchronously sending the foo message to Bob. She's invoking Bob's foo method. She's passing the argument Carol as a component of the message, and she's recording the fact that the result of the message should be placed in Alice's Dave variable.
Recording, what do you mean by that?
So what I mean by that is this black dot at the back of the message is basically saying the continuation of delivering this message should take the result of the operation and use it to fill in this Dave variable, which is shown over here with this purple circle and not yet live. So so now I'm going to go beyond what I normally say in the talk. So part of what I'm doing here with this slide is I'm kind of introducing the visual language that I'll be using throughout the talk, but I'm introducing it first to explain something that everybody already knows in their bones, so they get to to understand the language as related to something they already know before I use it to explain something they don't already know. Okay, so if Bob responds to the foo message by successfully returning Dave as the value, next, then in the success case, that returned value, Dave, is used to fill in the Dave variable. So the Dave variable now holds a reference to Dave. Next. But let's say Bob, Carol, and Dave are on a remote machine instead. In that case, Alice must use, Alice must use the eventual send, which is shown as this infix bang. So with the Q library, wherever you can write a dot normally in JavaScript, you can write a bang instead, and the infix bang makes the operation asynchronous. So over here, we're still sending the message foo to Bob. Alice is still sending the message foo to Bob, but she's sending it asynchronously. She's queuing up the message to eventually be delivered to Bob, and the eventual send expression immediately returns a promise for what the result will be. And this promise is shown as this black arrow, where there's no object attached to the arrowhead because it's not yet determined what object this reference designates. Rather, there's a halo shown around the arrowhead, which is what we call the resolver of the promise, which is the right to determine what object this reference does designate. Since Alice has immediately continued holding this reference to some object yet to be determined, next, she can use that reference to send more asynchronous messages, such as this bar message. We call that promise pipelining. In the success case, where Bob once again responds to the foo message by returning Dave as the success result, next, that's used to fulfill the first promise. The bar message now knows where to go, and it can be delivered to Dave. On the other hand, next, if Bob's foo method throws an exception instead, next, that exception breaks the promise for the result, causing the promise to be resolved to broken, with the thrown exception recorded as the reason for breakage. The bar message now has nowhere to go, so we throw it away, next, resolving the promise for its return result to broken for the same reason. We call this broken promise contagion. Next. The when catch expression is how we register for notification that a promise has been resolved. So the when part takes two arguments, which are the two callbacks, the success callback and the failure callback. Next. This code is exactly the same code, but we've changed the layout to emphasize the analogy with try-catch. When the promise that we're watching resolves successfully, next, to some value, the when reacts by invoking the success callback, next, with the promise's successful resolution as the argument, and it also resolves the promise for the result of the when expression as a whole to the value that the success callback returns. And we're done. On the other hand, next, I'm sorry, I forgot to say next with the and we're done.
That's okay, I'm following.
Okay. On the other hand, if the promise that we're watching next becomes broken, next, then we invoke the failure callback with the reason for breakage as argument, and once again resolve the promise for the result of the when expression as a whole to the value that the failure callback returns. Next. And we're done. Next. And finally, the defer expression simply makes a fresh promise resolver pair and returns a record containing the two sides. Next. Actually, can I have a glass of water or something? I always get dry mouth while I'm speaking.
Be right back. I'll get it.
I get it.
I know where it is.
Oh, okay.
You
You
don't.
probably know better than I do. I followed everything. It seems very high density. Well, I don't know whether you're presuming that people already know promises.
I'm not presuming that they were
Okay,
good
then
promises.
you've gotten, I think, an hour and a half of thinking to do so far.
Okay, so
But it's good.
So are there particular things where you would recommend I spend more time for an audience that is less, and is there more to say, or do I just need to let it sink in?
You're presenting when catch as primitive. Was that a deliberate choice?
Yes, I mean it's primitive in the sense that I'm not. I mean, it's all implemented in JavaScript, as is the eventual send. I mean, the entire Q library is a library. So I did say it was a library going in, but I'm presenting it as primitive in the sense that
The reason I asked the question is that I think I only really got how promise pipelining really worked when I realized from your thesis that when catch wasn't primitive.
Ah, interesting.
You know, having studied a little bit of processor design, I suddenly became much more comfortable with promise pipelining when I realized that processor designers sometimes do this with a handful of flip-flops. It suddenly didn't become terrifying.
Mm-hmm. Yeah, and the broken promise contagion, which is sort of the critical insight for bringing the whole promise pipelining thing together, that was actually inspired by the floating point NAN, the non-signaling NAN.
Yes.
Which turns out to have been invented. I found this out in doing the literature search for my thesis. It was originally invented by Konrad Zuse for the Z3. He had a three-stage deep floating point pipeline, and he invented the NAN in order to be able to report errors accurately without disrupting the pipeline. So it really follows.
Yeah, it's amazing how much the Zuse machines pioneered.
Yeah.
They're really quite impressive.
Mm-hmm.
Water is easy. Cracking down the cups is not.
Ah, thank you. Okay.
We're on slide labeled Q.all.
Yes, the first of those slides. So, using only these primitives, we can build a wide range of useful abstractions. For example, here's the Q.all abstraction, which in fact we go ahead and bundle as a convenience with the Q library. And what this does is the Q.all of a list of promises immediately returns a promise for the same list in which all of those promises are fulfilled, are resolved successfully. So how does it work? During the call to Q.all, what it does is it uses this for each and this when simply to set up, to register callbacks watching each of the input promises. And then next, Next, as each of the input promises resolve, next, it invokes the appropriate callback, in this case the success callback, next, 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 until the last promise resolves, in which case the success callback counts down that counter to 0, resolving the promise for the result to the list of promises which have been successfully resolved. Next. On the other hand, next, if any of the promises becomes broken, next, then the failure callback, next, gets invoked, resolving the result promise, next, to be similarly broken without waiting for the remaining promises to resolve. Next. And we're done. Next. So I'm now on the bank.
Before you go on
Yeah, question two.
on that last example. So some of the go back a little more. Okay. So in this picture, one of the promises has been resolved, and actions have been taken on that end. Right? But another one has failed, and that has caused other things not to happen. That sounds like a...
and forever abandoned, I believe.
Yes, but this one is not abandoned. And in fact,
Yes.
the unresolved one is not abandoned. It may resolve correctly, too.
That's right.
Right? And this sounds like a logic trap that you could easily make mistakes with.
In what way?
Because when you fire them off, you're expecting a set of things to happen. Only a subset did.
Yes.
You know that only a subset did, and you know which ones did not. But it seems like it's
Actually,
a
because of
potential
the
source of error.
so
Well,
because of the
actually-
asynchrony, the only thing that you know is that one of them failed.
That's right. But
Yeah.
right. But
If you compare this primitive with something called deferred list in Twisted, and a deferred list will give you a list of pairs saying whether each particular result resolved or failed. And that's sometimes more useful if you need it to.
I can imagine I can imagine recording that information here. It's not in Q.R. But it just seems that it's an easy mistake to make, where one of them completing and another one not could lead to a logic error.
So one very important point is Q.all is simply is a simple piece of code written using only the primitives you've already seen.
As I said, you could.
So if you want other other patterns, other abstractions that do for example what the twisted things is, it's a simple piece of code. But the other thing is that in practice, I find this is the more useful primitive. That E has, this corresponds to what in E is called promise all fulfilled. E also has a promise all resolved, which is more like the twisted primitive, and I just don't find it to be as useful. Brian, since you have the most
in Tahoe, we end up using the primitive to just give you one failure more often as well.
So in terms of your use of twisted, your experience says that Q.all is really the right useful primitive to present.
Yes, you gather results, which is equivalent to Q.all.
Good.
I think it does tend to be more useful than the wait for all resolved. But what I've also noticed in all the coding that I've done is that I've gone through and removed those in favor of some more explicit state machine, because I find that waiting for a bunch of things to resolve ended up introducing a bunch of stalls or losing the opportunity to switch to a better server or a better source of progress. So I did find it was one of those tempting things that I reached for initially, and now I'm tending to look for other control structures.
Interesting. Okay.
Yeah, quite often waiting until all of the results are resolved is waiting longer than you need it to.
Okay?
And we do keep running into problems where a server will silently hang, and we have to wait for TCP to time out, which can take anywhere from 15 minutes to a couple of days. And that's a case where a control structure that has an explicit, I'm impatient for this result, it's time to go and try something else, tends to work better. And that I found wasn't very easy to implement with sort of deferred to promises. It ended up being a more explicit state machine. I have one more question.
Yeah.
It was obvious to me just reading through this. When you have a resolved promise in the Q library, how do you get the result from it?
With the when.
So in this case, when Q.all gives you a promise that fires with a list of promises, do you have to do another when on the insides of those promises to get at a real value?
So this, I'm taking a
I know
bit.
it turns.
Yeah, I'm taking actually a bit of a shortcut in the actual code on this slide. In this talk, I'm not really making a strong distinction between a promise that's resolved to a value and the value itself. So
Yeah, you're kind of not actually getting value in many cases.
yeah, so the actual Q.all bundled with the Q library actually accumulates where you see the underbar in the success continuation.
Just adding that to the list, turning the list.
What I do is I actually create a new list. I don't just return the answer. I don't resolve to the answer P's list. I create a new list on initialization. I fill it in on each success continuation, which means also that I need the indices in order to know where to fill it in.
I was confused by that as well. I was confused in the same way as Brian.
Yeah, and it's.
I was expecting the code to be more complicated. I thought, hang on, there's something missing here. But maybe only people who have actually looked at the internal promise libraries would have that problem.
I think that's the case because no other audience has noticed that. And for the use that I'm making of this primitive in this talk, as you'll see, this is adequate. And the reason, and part of the reason it feels natural to me is that coming from E, the resolution of a promise, a resolved promise is its resolution. Once the promise resolves, it's indistinguishable from its resolution. So the corresponding code in E is actually accurate. But for JavaScript, this is definitely a shortcut that's not reflected in the real Q library.
In the Q library, is when the only way of getting the real value out of it?
No, there's also a what Tyler called a Q.near, and in my ECMAScript draft proposal, I called it Q.nearer, which is more accurate. Because it gives you the value that's the most resolved form of the promise. If it's still an unresolved promise, it gives you back an unresolved promise, which is why I called it nearer.
I think Tyler gives you an exception, right? If it's not resolved. If it's far, you do it.
I didn't think so, but I don't remember anymore. In any case, one can argue that making use of Q.near or Q.nearer in code is a poor idea compared to just using when to get the results back.
Stigler has this commuter.
Yeah, because if you do that, you have to keep track of the state that this is an already resolved thing.
Right.
Yeah.
But Stigler has made good use of the commuter pattern where he switches an object between near and far.
Mm-hmm.
And I don't recall the exact examples, but you should ask him about it.
Okay. Yeah. So in this,
I think that the intuitive objection to just using when is to do with the overhead of using functions in JavaScript and this.
No, it's a matter of
overhead than.
No, it's also a matter of sequence and control, because if it's near, you can make an immediate call on it.
Oh, good point. Yeah, because when may be in a future time, whereas nearer is in this time.
Right, but the problem is, when do you know that a promise has become near? Well, generally the way you know is during some later turn, which happens at such a which only happens at such a time that the promise has become near, and that's sort of exactly what happens during the success clause of a when.
Right, but Stigler is using
Yeah.
this to.
So in other words, instead of keeping track in the programmer's mind of promises that are actually resolved, you should be converting those into resolved values and passing those around.
Yeah.
But there are times when you want a sequence of operations to complete within a turn, and that's where he's using the near.
But how did it come to be the case that the promise is near during that
I think you can
turn?
always rewrite code that doesn't use that uses nearer to code that doesn't.
I don't know. We have to ask Stigler.
Okay, but what part of what I'm trying to do here
Right.
is to be as minimal as possible while still showing off something very impressive expressed in very few lines of code.
Well, I want to see how this applies to the point you're trying to make.
Right.
That's the important thing.
Okay, good. So let's go on to that. So let's go on to the first slide labeled bank. So now we have our first application code towards the goal of expressing secure distributed escrow exchange. This code expresses much of the logic of a secure money. I'm not going to explain how this code works during this talk. I do explain this code in detail in other talks available on the web, and those other talks explain precisely what the security properties of this are and the sense in which it's secure. Next, today I'll only talk about how this code is used from the perspective of its clients. In this scenario, Alice and Bob, there's three parties, Alice, Bob, and the bank. The bank is the gray box shown at the bottom of the slide. And in the scenario, Alice and Bob do not trust each other. The bank does not trust Alice and Bob. Alice and Bob trust the bank with their money and nothing else. And Alice wishes to buy something from Bob for $10. And Alice is willing to risk her $10 on the possibility of Bob's non-delivery. However, Bob wants to be sure that he's really got the $10 before he releases the good in exchange. That's the problem
It's an eBay problem.
Yeah, this is the problem that this slide is trying to solve. So in this protocol, what Alice does next is she uses these three lines of code to create an empty payment purse, to transfer $10 from her main purse into her payment purse, and to send that payment purse to Bob in this buy message with a description of what she wants to buy. And as a result of eventual sending the buy message, she's immediately holding a promise for the good that she hopes Bob will release in exchange. Bob, on receiving the buy message, has no idea what that payment argument is. It's just some random object from somebody he doesn't trust. It could be anything. So Bob, in order to deal with the security problems that arise, delegates all those security problems to the bank, which is the code you saw on the previous slide, and he delegates those with the underlying piece of code, which sends the deposit message to his main purse at the bank, with the payment purse as argument, and his main purse, if it deposits the money successfully, next, will acknowledge success by resolving the promise for the result of the deposit successfully, in which case Bob's success callback runs, releasing the good in exchange, which resolves Alice's promise for the good. Next.
Can I just make a comment before you carry on?
Sure.
It might be clearer if the code on the right-hand side was in a sort of def by paren desk payment P, so that you can see where that this is in an invocation of buy.
We don't see description on the right-hand side.
Right.
How does he know what good is being purchased?
Right, right. I didn't show the whole message. I just showed the part dealing with the payment, the incoming payment purse. So you're right. It'll blow up the code on the right past 3 lines, but it's the right thing to do.
I think it kind of is necessary.
Yeah, I think you're right. Okay.
Is it the case that the good is being returned to the bank before being returned to Alice?
No.
This is not an escrow.
I mean, I know that's not intended. I'm trying to read through the code and make it clear to myself that.
Yeah, what's going on is that the deposit message is being sent to the bank. The code executing in Bob is holding a promise for the result of the deposit. The when is happening within Bob. So when the promise for the result of the promise resolves successfully, the when in Bob is resolving is calling the callback and then resolving the result for the result of the callback. So yeah, there's this outer method which is the buy method, and it's really ultimately resolving the promise for the result of the buy method. So that's all between Alice and Bob. It's not going back through the bank.
So in the
So the good is actually
when you
return call.
I'm sorry, Brian, what?
The good is bubbling up those 3 return calls. It never actually leaves Bob until it goes back to Alice's original promise.
That's right.
so
when you were explaining the when construct before, did you explain that the return value of the callback function gets propagated to the return of the when? Because I don't remember that.
So I did.
I mean,
I did say it, but I said it kind of quickly, so it's easy for it to have been lost.
Okay.
Let's back up to that slide. Okay. So back up to the slide where it says try catch like layout under when catch expression.
yeah.
Okay, so next, success case. Next,
Yeah.
so this is the slide where I talked that through. I said that it invokes the success
yeah, okay.
callback
So,
with the promise's resolution as argument and resolves the result of the when expression as a whole to the value returned by the success callback. And that's shown by the black arrow's resolver being carried in the continuation slot of the message invoking the success callback.
should that be labeled results P on the left?
Yes, it should. I mean, that's a good point. I think that would make the correspondence between the code and the diagram clearer.
now, at an earlier,
Okay, yeah.
earlier point, you introduced the promise resolver pair
Yes.
and the explicit resolve state.
Mm-hmm.
I actually think that all these examples would be clearer to the novice that way. Rather than mysteriously returning a value, say, I have the resolver, I'm going to resolve the promise to this value.
Oh, that's good. Just do the q dot defer first instead of last.
Yeah,
I think that's good.
I think that would help.
Yeah. Yeah.
This is kind of a mysterious mechanism.
That's part of what I was saying when I said that I only really got promise pipelining when I saw when catch as being
Ah.
non-primitive.
So anyway, do you think about
Okay, good, good. And q dot defer is, of the 3 primitives, by far the simplest.
Yeah.
So that's another reason to put
Yeah.
it first. Okay, that's good. Okay, so back up to the so let's go back. Let's go forward again to the last of the money slides.
That's 44. 45.
Is that called the 5 players or the slide before that?
The slide right before that.
Yeah.
Then see here, what you do is you just resolve the problem. You use the resolve of good.
Well, I would still have the code be of this form,
But
but I think doing the slides in that order does help. I think that's good. Okay. So in any case, so having completed the money example, the thing that I forgot to say here, which I'm now going to say, but the scenario has one deficiency compared to what we might ideally like, which is that Alice had to risk her $10 on the possibility of Bob's non-payment. So we address that in the same way we do in the real world, next, by introducing escrow exchange. So in this scenario, let's say that Alice and Bob are trying to exchange stock for money. And in this scenario, we have 5 players. In the upper left, the dollar issuer is precisely the bank that we just saw. The stock issuer in the upper right is another instance of the same code, but run by a separate institution and with the units representing stock rather than money.
The stock is what is being bought.
The stock is what is being bought by Alice, right? It's Alice's money in exchange for Bob's stock. And in the scenario, Alice and Bob again do not trust each other. To make the scenario sufficiently challenging, the dollar issuer does not trust any of the other 4 players. The stock issuer does not trust any of the other 4 players. The escrow exchange agent does not trust any of the other 4 players. And Alice and Bob each trust the other 3 players to play their respective roles in this protocol, but with nothing else. So in the scenario, let's say, next, that the escrow exchange agent, next, succeeds at escrowing Alice's money, next, succeeds, next, at escrowing Bob's stock, next, and the escrow exchange, seeing that both escrowings succeeded, next, proceeds, next, to deposit deposit Bob's stock into Alice's account, next, and to deposit Alice's money into Bob's account, next, and we're done. On the other hand, next, let's say that the escrow exchange agent happens to succeed at escrowing Alice's money, next, next, but for whatever reason, next, fails to escrow Bob's stock, next. The escrow exchange agent as a whole, seeing that one of the escrowings failed, next, proceeds to refund Alice's money, next, and we're done, next, next. So how do we represent this as code? So the general pattern for expressing the 2-phase commit transaction coordinator using promises is that the transaction coordinator first creates a promise, the decision promise, whose resolution represents the decision about whether the transaction should commit or abort. It then instantiates each of the participants, that's the calls to participant A and participant B. Each participant immediately returns a promise whose resolution, whose eventual resolution indicates whether their phase 1 completed successfully or in failure. And then the transaction coordinator simply does an all of the promises for each of those phase 1s in order to decide whether the transaction as a whole should commit or abort. Next.
Each participant
Can you go back?
Yes.
So you are resolving to a promise. Is that correct?
You're resolving the decision promise according to the result of the all.
But Q.all returns a promise.
Yes,
Right? So you're resolving a promise to a promise.
that's correct.
Okay, this is a subtlety that you haven't mentioned.
Mm-hmm.
Significant.
Mm-hmm.
And it's related to the change,
Well-
the promise pipelining that you mentioned earlier that sort of dropped. So maybe this is a place to point out.
Mm-hmm. So when you resolve the decision promise to this other promise, it means that however the other promise resolved, the decision promise resolves
And I think
identically.
it's worth calling out.
Okay. Yeah, David, Sarah, you were going to say?
I was just going to say that you had already mentioned that point in the description of Q.all, but yes, this is a good time to reiterate it.
But I don't think he resolved, he put the promise from the Q.all directly into a resolver in that example. Here he does.
Right, and in the Q.all case, within the Q.all, I resolve the promise to a list,
that is something
but I
else.
don't resolve the promise to a promise. This is
Right.
the first time that I
That's
resolve
right,
a promise
and
to a
I think
promise.
it's worth pointing out.
Yeah. Okay. So on the first slide labeled general 2PC pattern -- participant. So the general participant pattern, let's start at the bottom, it initiates whatever its phase 1 is, but it immediately returns a promise indicating whether the phase 1 succeeded. And then in the middle, it sets up for phase 2 by registering on the decision about whether the two-phase commit as a whole commits or aborts. It registers an on-commit action and an on-abort action. Next. So the overall picture of the escrow exchange agent is that the transaction coordinator is mostly just the all, which watches for the result of the phase 1 from each participant, and then feeds back the decision about whether the transaction as a whole should commit or abort, feeds that back into each participant that watches that decision in order to then proceed to commit or abort. Now let me break from the normal presentation and point out something very crucial here, which is here's where I'm really relying on the Ken failure model as opposed to the E failure model, which is it's really crucial that both participants see the same decision.
Yes.
I mean, in this code, the coordinator and the participants themselves are all in the same VATs. It's the things feeding the participants which are in other VATs. So in fact, the E-failure model would work here. But it's a slight adjustment to the code to have the participants themselves in separate VATs, which you might want to do, for example, for scalability. But that only works under the Waterkin failure model, because under the E-failure model, if you put the participants in separate VATs, a participant could cause one to see failure while the other sees success, in which case this is no longer two-phase commit.
Now, the phase 1 result
Mm-hmm.
is coming from a component of the escrow agent, correct?
It's coming from the participants are. Let's back up to the slot to the slide with the escrow exchange agent diagram. Let's say failed exchange. So it's the participants are the two diagonal boxes. So one is responsible for transfer. One is trying to transfer the money from Alice to Bob, and the other is trying to transfer the stock from Bob to Alice. And it's on the way to the transferring which they do the escrow, and that's the phase 1.
I'm just wondering who's responsible for resolving the promise from each participant. If it's Alice or Bob, you're toast. So that's why I was asking where that's happening.
Okay, so
I think perhaps the word participant doesn't indicate sufficiently who's doing this.
Yes,
Because the
Yeah,
participants
there-
could mean the clients themselves, rather than a representative of the client in the exchange agent.
that's true. Right. So that was
I don't
actually.
know what better name there is for that.
Yeah, that was actually an interesting discovery in doing this, which is the participants, as far as the two-phase commit are concerned, the normal terminology of two-phase commit, are the money transfer agent and the stock transfer agent, both of which are part of the escrow exchange agent. Whereas in another sense, Alice and Bob are the participants in the escrow exchange. And that separation was part of the discovery here.
Okay, but it's not clear from your naming or your examples who is returning this, resolving those two promises.
That's correct.
And so we need to clarify that.
It's clear from the diagram, but it only occurs in one place. It's not re-emphasized anywhere.
Yep.
Okay, now,
Yeah. So in that sense, you can think of escrow exchange as a special case of two-phase commit, but the correspondence between the two problems is deeper than that. And the reason it's deeper is that what is two-phase commit really about? Well, the general problem that two-phase commit, the general pattern of two-phase commit is that in phase one, what each of the participants do is they reserve some resource. They try to reserve some resource. They indicate as the outcome of phase one whether the resource has been successfully reserved. And if all of the participants successfully reserve the resource, then in the second phase, they proceed to employ the resource. Well, so in that case, with that general understanding of what two-phase commit means, what does two-phase commit among mutually suspicious party means? Well, under mutual suspicion, reserving a resource must mean that you're transferring the exclusive right of the resource into escrow, into some holding of the right which is mutually acceptable to the participants. So in that sense, Alice and Bob actually are the participants in this more general understanding of two-phase commit.
That was not my question.
I know, I'm answering a different question.
Yes, my question was, who is deciding the state of the resolution of the phase one? It cannot be Alice and Bob.
No, escrow.
It has to be the escrow, a component of the escrow.
It's a component of the escrow agent.
And I'm saying that was not clear from the lead up to this picture.
So it's a component of the escrow agent, but it's determined based on
Yes.
the inputs from Alice and Bob.
I'm simply saying, who does the resolved statement? It cannot be Alice or Bob because they could lie.
Mhm.
That's all.
Okay.
And I'm saying that was not
Right.
made explicit on this picture.
Right, and it's so that's actually a good segue for something that's about to come up. I'm not quite there yet, but there's two ways in which the code I'm about to present is vulnerable to lying from Alice and Bob, both of which I'll first present the vulnerabilities and then address them. Okay.
I have a question, but I think I'll defer it until we discuss it.
Well, go ahead and mention it just in case we lose it.
There's a result in distributed computing theory that says that if you have a fully asynchronous protocol, in other words, you can't bound the time until you get a result from any given operation, then it's impossible to implement consensus.
Okay.
Consensus has safety but not liveness. That's a general
It's
result.
Yeah.
Okay. So
this is obviously a kind of consensus problem.
yeah. So if the network partitions during the window of vulnerability in two-phase commit, then the two-phase commit itself is stuck, and that certainly is the case here, because the whole thing rests on top of the CAN protocol. Everything simply resumes without other failure handling.
Well,
But there's a different delay problem, which I'm going to come back to at the end of the talk.
It's like the phase 2 IPO for Facebook, and that is that some people didn't know whether they owned stock for quite a while.
That's right.
No big deal.
By the way, I've been doing some work on distributed commit.
Uh-huh.
I understand the failure modes of two-phase commit. There is a failure mode of two-phase commit that leads to inconsistency.
Inconsistency.
Which is the reason three-phase commit was developed.
To inconsistency.
Yes.
So if you can point out, this one is just two-phase commit. I thought if you can point out where the possibility of inconsistency here is, I'd be very curious.
It's in the three-phase. It's in the introduction to the three-phase commit paper. What happens is there is a certain point at which both the coordinator and one of the participants fails, and on recovery, you can't result. You don't know whether the decision was committed or not, and it's described in that three-phase commit paper.
So over here,
it's different here because you have the nature of terms, and you have the Ken reliability. I'm just pointing out that in the general. So it's worth making sure you don't have that inconsistency.
If the escrow agent fails unrecoverably, then I think there is a problem in that case.
Because you may not refund the money.
No. What happens is in real two-phase commit, if the coordinator fails, you start a new coordinator.
So having looked up the definition of two-phase commit, the definition of two-phase commit is actually silent on that issue. It assumes the general definition just assumes one coordinator and assumes it eventually comes back up.
But the point is that the state, when you start a new coordinator, the state is preserved. So the new coordinator has the state of the original one. So that is correct. The issue is if the first coordinator now recovers, you have to resolve the fact that there are two coordinators sending repair messages.
Okay.
And so it's really amazingly complex.
Well, the coordinator is a single
point
of
failure. I think the Ken protocol does simplify this because it guarantees that there's
what happens is this issue about for each VAT there's exactly one restart. That you never have two revivals of one VAT is actually one of the difficult requirements, but it's a requirement on the infrastructure for running Ken correctly.
Correct.
If you got two revivals of one VAT from the same checkpoint, you void the warranty on all the Ken results.
My recollection is that having the multiple coordinators is not the source of the inconsistency. It's that, and it may have to do with a lost message, but I don't recall because I haven't looked at it for a year.
And I can't remember exactly how this result about asynchronous protocols would apply to this case. I'm going to have to think about it a lot more.
There is a paper on three-phase commit. That paper explains the problem beautifully. I don't recall the details. It gave me a headache when I read it the first time.
And do they claim that there's no need for a four-phase commit?
The interesting thing is there is no proof of safety for three-phase commit.
Wow.
That's pointed out in the Paxos commit paper.
Okay. So
Paxos, though, doesn't have Leibniz.
One of the things that's interesting about this is that I require the Ken semantics for each VAT, but it doesn't have to be achieved through the Ken mechanism. For a VAT like the escrow exchange agent, having a Paxos-based redundant implementation of the state machine, if you can get the full Ken semantics, reliability semantics, and even better, did you see the thread on Cap Talk that Kevin Reed started about trying to make use of Bitcoin-like mechanisms to do a distributed implementation of a VAT?
Yeah, but that petered out pretty quickly.
Yes, it did, but did it peter out for any reason other than it's hard to think about?
I don't think anybody else understood what Deli was talking about. That was my impression.
Okay.
Anyway.
Did you guys on the phone, did you guys follow that Cap Talk thread?
It's a while back.
I did see it, but I didn't think about it deeply enough to contribute.
Okay.
I don't remember it. I do remember someone mentioning that, but I don't remember any detail.
Okay, please take a look at it, because I think the idea of trying to make use of Bitcoin style distributed commit for general purpose computation is a really fascinating idea, and if it actually can be made to work out, very promising.
Okay, anyway, my point
There's
on
a
this.
guy. There's a guy named Andrew Miller who participates in the Tahoe mailing list who's been doing a lot of study of trying to model Bitcoin as a more as an authentication system or as a distributed consistency thing. So we should probably get him involved.
Okay, cool.
So my point here is, make sure you understand that failure mode of two-phase commit, because I'm not certain that Ken reliability is sufficient to avoid it.
Okay.
Okay?
Okay. Okay. So, the general two-phase, general 2PC pattern slide. I'm going to, with the diagram, I'm going to the next slide after that, labeled exchange in 7 lines. Is everybody there?
The one that says
Yeah.
Okay. So, so filling in the transaction coordinator pattern for the escrow exchange agent, the escrow exchange agent gets this record from Alice named arg-A, this record from Bob named arg-B, makes the decision, and then just invokes the transfer agent, the first transfer agent, to transfer Alice's money to Bob, the amount of Bob that...
One minor point, you said makes the decision. That has a very different connotation than creates a decision promise resolver pair. When you said makes a decision, I said, oh, he decides. That's not what you mean.
Well, it is what I mean.
No, he's making a promise resolver pair to represent the decision.
Okay,
You
but
said
then he...
makes a decision.
I see.
When I make a decision,
makes a decision promise. That's right.
Okay.
That's right. And in any case, creates a first transfer agent for transferring from Alice to Bob the amount of money that Bob demands, and makes a second transfer agent for transferring from Bob to Alice the amount of stock that Alice demands. Okay. Filling in the transaction participant code, start at the bottom again. In phase 1, the participant escrows. Let's talk through the money case. Escrows Alice's money by depositing it into the escrow purse, and then now go to the middle. Sets up for phase 2 by registering on the decision a on-commit action, which deposits that money from escrow into Bob's account, and sets up a failure action that takes the money that was escrowed and refunds it to Alice. Now, there's one problem with this, which is, next, this code suffers from a massive security hole, which is, where did the transfer agent get the escrow purse? Well, in this code, it just asked Alice for it. But we don't trust Alice. Alice's source purse, being potentially dishonest, could return an escrow purse that lies in response to the deposit message, misleading this code such that Alice gets Bob's stock without spending any money. We can't solve the problem by just asking Bob's purse for an escrow purse instead, because then that leaves us with the opposite security hole. So what we really need is an escrow purse which is mutually acceptable to Alice and Bob. Next. To implement the logic of mutual acceptability, we introduce one new primitive, which is the join primitive, which is our primitive for distributed equality, where the join of two promises immediately returns a promise for the one object that they both designate. So if the two input promises eventually resolve to both designate the same object, then the result promise resolves to designate the same object. And if the input promises resolve in any other manner, then the output promise breaks without delivering any of the messages that were sent to it.
Synergy, distributed synergy.
Yep.
Now, what would Dean say about this?
Dean would say that you don't need this equality primitive. And my answer is, perhaps you don't need it, but
If you have Dean on your staff.
but if you have Dean on your staff, and even with Dean on your staff, the solution to distributed escrow exchange agent is no longer 43 lines of code. So part of the
Well, it's possible to have join be the primitive rather than EQ be the primitive.
Yes, that's correct. And that's actually why I say here that even though I show code implementing join, why I describe it as a primitive. And this was, I was at a programming language conference, one of the places I gave sort of this talk. William Cook and Phil Wadler both strongly objected to EQ itself, object identity being a primitive. And once, after about an hour of talking about it, we had an hour-long conversation about distributed EQ. And I realized at the end, after about an hour of conversation, that join as taken as a primitive rather than as something built out of EQ has most of the virtues of EQ and fewer of the downsides, although it has some.
Now, I think join as the primitive is clearer as well.
Yeah. And Phil and William Cook both still objected to join, but only a small fraction of their objections to EQ still applied. And that was very clarifying for me.
I think I have objections to EQ that don't apply at all to join.
That's wonderful. Can you state what they are? Because unfortunately, the conversation we had about this at Dagstuhl was not recorded, and I've had trouble reconstructing it. So please.
Let me think. Let me try and reconstruct my reasoning on this.
Well, he's thinking.
I'm going to think about this some more. I'm writing a note because I'm mailing this afterwards,
So,
explaining why I don't like EQ.
so I wonder if join as the primitive could also resolve the issue when dealing with membranes, because it's got access as a primitive to lower level data structures. You know, if you send a reference through a membrane and it comes back in, right? You've got this issue is EQ won't work, but perhaps join as a primitive could do it. I'm just occurred to me.
I remember the main reason I don't like EQ is that it defeats transparent forwarding.
That's the membrane issue. And perhaps as a low-level primitive, you can resolve that problem.
So join does or does not defeat transparent forwarding, depending on
Yes, I've heard that argument about forwarding before, but I have not heard specific use cases. The danger that is proposed is that someone compare the real and the forwarded thing and discovered they're different. They are different, and it's important.
Well, no, the main danger is that having access to an equality primitive that works on all references means that you get, let me think about this, you're sort of exposing implementation details.
The cases that I wanted for, the position that you're afraid of exposing to, the person that you're afraid will discover the thing is not in a position to do so because he lacks the real one. So he can't compare the fake one with the real.
No. I'm saying if I send a reference to you
Yes.
through a forwarder, and you send it back to me,
Yes.
do I know what you sent back to me is what I sent to you?
Well, you would if you have EQ.
Right. But
And
you
you-
would
and
if
you-
I
and-
joined,
And you would if you have joined.
and I would if I have Ask Bob.
And so you discover something you should not be able to
So hold
discover.
on.
But-
Hold on. Ask Bob. Ask Bob is weaker than
That's
join
weaker, yes.
because Ask Bob is
And
not
why?
adequate for mutual acceptability.
That's right.
And
right.
that's why this is.
Exactly.
I mean, this is really just, in some sense, a recapitulation of history, because it's essentially the distributed escrow exchange agent problem in which I first encountered the need for the hard need for EQ,
Mhm.
and it's the grant matcher problem that Norm abstracted. He abstracted from essentially the problem that we're presenting.
My point is that I think we've always had this issue about through membranes, through forwarders, and perhaps join as a primitive can address them, whereas join as a construct cannot.
Worth examining.
Worth examining.
It'll have different. Yeah.
Just a question.
To abuse EQ of X and Y, you have to both hold X
Yes.
and Y.
Yes, I gave you an example.
Okay, the problem is that it may be difficult for a membrane to preserve identity. In the local case, it's simple for a membrane to preserve identity. It just needs a map of wrap things to unwrap things.
I am asking a question, not answering it. I'm saying
Okay.
perhaps as a low-level mechanism, you can use join to do that. I don't know.
Okay, so I'm going to go on past this slide now. So next, in order to make use of this, we need to enhance our notion of the bank in one way, which is the bank uses these additional 3 lines of code to create a single make purse function, and all customers of the same bank, really of the same currency at the same bank, they all get the same make purse function, so that Alice and Bob can each take their make purse function, hand it back to the escrow exchange agent, and the escrow exchange agent can see that they agree.
If they've agreed on the currency.
That's right. Okay, next. So we take our previous transfer agent, which is the code in gray, and we parameterize it by the mutually acceptable make purse function in order to make a mutually acceptable escrow purse. Next.
So can you go back?
Yeah.
Who's executing this code?
This is still code executed by the escrow exchange agent. Okay.
I have another question. Is the bank checking a brand or something on the original purse to make sure it's one of their own?
Let's go back to the bank slide.
They both have the same make purse function, but that doesn't guarantee that the purses are going to behave the right way. The input purse.
So let's go to the slide bank, 17 lines, money as factorial.
I think if they agree on the same currency effectively, then they're agreeing to trust the same bank.
Right.
Yeah, what I don't get is that because all purses come from other purses, that Alice and Bob may have the same make purse function, but they pass in a doctored purse.
No, they're not they can pass in a doctored purse when they. So okay, let's say they do that. Let's go back to. Sorry, I'm flipping slides like crazy. Okay, let's go back to transfer 9 lines insecure. Let's go forward. I'm sorry. Make transfer plus 1 line secure. So we're at the bottom in phase 1. We're asking the escrow exchange agent to do the deposit. The escrow exchange agent is itself. I'm sorry, not the escrow exchange agent. We're asking the escrow purse to do the deposit, the escrow purse was made by the make purse function, which Alice and Bob agreed on. So the escrow purse which it makes must be mutually acceptable to Alice and Bob as being a purse that they agree on.
Okay, the argument is passed into make purse maker, not into make purse. And that original purse is an empty purse.
The argument is...
It's hard that we're not looking at the same thing. I'm looking
No. Sorry. And the make purse maker piece of code, this is code that's used by the bank to make a make purse function. So,
right, and so it's using some primordial purse that's empty that...
it doesn't matter.
Just
It doesn't matter whether it's empty.
Okay.
It's
right.
asking. It's asking any purse that the bank has a hold of, but it's a purse of that currency. It's a non-doctored purse. It's a purse that the bank holds, so the bank trusts its own purse.
Got it.
And it
But
makes.
how does the bank know that make purse maker has been passed one of its own purses?
The bank
Here's
runs
the
Mace.
profile.
The bank is.
Oh,
The bank is running make purse maker once during initialization. In order to make a single,
Oh, okay, right, yeah.
it's making a single
It's
make
making a
purse
It's
function.
making a purse factor.
Right, it's making a single make purse function, and then it gives all customers the same make purse function. So this code is executed before the bank has any customers.
I confused
It would probably be clearer to put that on that slide, the one entitled Make Purse Maker 3 lines.
I'm thinking it might be clear if the bank had a way of making purses from nothing instead of only making them from other purses. Of course, sort of a bootstrap question of where does a primordial purse come from? I
Yeah.
misinterpreted the make purse function
Yeah.
as the purse comes
You can just assume that the bank has that function rather than giving its implementation, because I think the implementation is more misleading there, I think.
Right, what I'm trying to do, though, is I'm trying to account for, as honestly as I can for all of the lines of application code needed to create
Yeah.
the secure distributed escrow exchange agent, so I'm counting this as 3 lines of code.
Oh, okay. Yeah, in that case, you need the explanation on the same slide.
Okay,
Of who's running this code.
good,
Right.
good.
That's
So,
two
and
lines
I've
of-
got plenty of room for explanation,
That's
so
two
that's
lines
good.
of code. You don't count
Yeah.
lines just as curly on it.
So I sort of do and I sort of don't. If we back up
Yeah,
to the join, I'm actually
I
counting.
would count that as 2 lines of code.
What you might do is have a picture of the bank here and kind of show this, initialization time make purse maker, and then show how any client of the bank can get access to the make purse function.
By the way, my rule is to count statements, basically semicolons, and that's a clearer count.
Mhm.
So what you want really is a Grand Vector diagram of the bank with Alice and Bob holding a reference to the make purse function that's been created by the bank.
Yep, supplementing this slide with a diagram I think would be a very good idea, and I certainly have room for it.
Okay.
Okay. I need to go to the bathroom. I'll be right back.
Okay.
So while I'm gone, everybody read the slide labeled Make Exchange, the Secure Escrow Exchange Agent. Plus 4 lines to secure, that line of code.
So I see an error right away. I think transfer money and transfer stock should each end in a capital P, because they are promises.
Sorry?
I think transfer money and transfer stock, bar transfer money, should be var transfer money P. That's a promise.
Sorry, I can't hear you at all.
Sorry.
Just a moment, I'll close the door. Someone's boiling kettle. Right, say that again.
the var transfer money, for example, should be a var transfer money P because that's a promise, isn't it?
No, it's returning the function.
That's a function. Oh,
Previous page.
gotcha. Right.
No, it is a promise because it's the result of a bang call, an eventual send.
Yeah. Let's see. So the join returns, q.join returns a promise.
Oh, sorry, yes.
So make transfer
I'm
returns a promise.
I'm reading the code wrong. It's returning the transfer function.
Right. So this should be, those should be promises.
No, when it's
Oh,
invoked,
no,
it
they're
returns
function.
promise.
That's right. When it's invoked, it returns a promise. So this is returning a function that gets invoked and returns a promise. Okay.
Okay.
We were arguing about whether transfer money is a promise or not.
It's not.
It's a function.
It's a function. It's the function made by the make transfer function on the previous slide. So this make transfer function just creates and returns a function. Okay. So over here in gray is again the transaction coordinator from the previous slide, and we've added. What we've done here is rather than using a generic transfer function, we use a one function for transferring money, another function for transferring stock. Let's focus on the money case. To make the transfer agent for transferring money, we make it using the make money purse function that Alice and Bob find mutually acceptable.
So now, if they agree, you get the one purse they agree on.
Right.
If they disagree,
Yes.
what happens?
Okay. I am so glad you asked. This is the thing that I think is so cool about this code. Hold on, I'm getting a phone call. Hi. Okay, I'm in the middle of a presentation, but I will do that. Bye. Okay. So let's follow through what happens, because to me, this is really what the answer to your question just now is the clearest symptom to me that this code demonstrates that I've got a good set of abstractions. Okay, so the q.join here on this slide will eventually resolve the promise that it returned to broken. Now let's go to the previous slide. That means this make escrow purse P eventually resolves to broken. The eventual call that we're making on it returned a promise for an escrow purse. That will eventually resolve to broken. At the bottom of the slide, we asked the escrow purse promise. We did an eventual send of this deposit message, returned a promise for the result of the deposit. Since this thing eventually resolves to broken, the promise for the result of the deposit will eventually resolve to broken, and that's just like a failed deposit.
Right.
It indicates phase one failed, and then the all seeing the all over in this slide, seeing a phase one failure, will proceed to decide that the transaction as a whole failed. So there's lots of different ways in which things can fail, and they all result in propagating failure into a failed decision, which rolls back the transaction.
The make transfer function returns a function.
That's right.
What function does it return in the join phase?
It returns this transfer function over here. This is the function that it returns. The join hasn't yet failed, right? It returns a function immediately. The join only fails eventually.
Okay.
So the transfer function itself then gets called immediately down here. The promise that it returns eventually resolves to broken if the join over here eventually fails.
I'm getting all twisted up, but let's go on.
Okay.
I could understand if you were returning a promise for a function, then it would be quite clear to me what would happen. But you're returning a function that inside of it is not yet executed, but
Well,
It has parameters and.
over here, the eventual send of the
Yeah, I
deposit
understand.
gets executed
It's
immediately.
just too many twists.
But the deposit, right?
It's just too many twists and turns for my brain to do without paper.
Yep.
Too many
Okay.
levels of hypothetical.
Okay, so that means I do understand the problem, even though I don't understand
Yes.
the answer.
Okay.
The diagram you had earlier, that general pattern with the sort of logic gate that loops back on itself, I thought that's a really good way of
Yeah.
following this.
Except in this case, you're returning a function that hasn't been evaluated yet, that the argument has, and it's causing something inside the function to be turned into something that gets turned into something else. Give me a headache.
Okay.
You understand my confusion?
Yes, I do. It would be nice to, so for that particular case, since it's really, I think, the clearest demonstration that this set of abstractions is more right than you might think at first. Because when I first coded this, I didn't think about that case explicitly, and it turned out to work
worked
for me.
anyway.
That's right.
That's always a good sign.
Yes.
Okay.
Anyway, so
Okay. So next, the slide labeled general 2PC pattern -- transaction stuck. Okay. So there's one remaining problem with the code that you're seeing, which is what happens if the escrow exchange agent escrows Alice's money, and then Bob simply never responds. Okay? The Alice's money is now just stuck in the escrow exchange agent. So
we know people that happen to.
yeah. So actually, since I underlined participant A here, I should say it the other way around. That Bob's stock is stuck in the escrow exchange agent if Alice never responds. So if participant...
Before we go on to that, can I just ask a question about the, so without loss of generality, the money needed argument? Are we assuming that that's an integer because we don't enforce that it's an integer and it's provided by B?
Okay.
We're passing that into a purse. What if it behaves like one integer at one point in time and another integer at another?
Mm.
Very good.
45 lines.
What does it for, right?
But you've got balance.
So it's actually so it actually would get rejected, but it's subtle. Take a look back at the bank slide.
Oh, right. The bank is enforcing that it's an integer.
Right, because the NAT, if provided with a non-integer, will fail.
Yeah, got it.
But that's a little subtle.
Okay, yeah, I'm happy with that.
Okay. Phew.
It might be useful to point that out.
Well, is that actually testing for integer or only something that acts like integer?
It's actually testing for integer. Fortunately, that's the more straightforward case in JavaScript. Okay, so going back to transaction stuck, if Alice's purse if Alice just never responds, then we've successfully, this participant A call, the promise it returns never resolves. Next, then the promise returned by Q.all might never resolve. Next, which means that the decision promise never resolves. So, before solving this, let's explain another useful convenience that's bundled with the Q library, but still just a convenience. It's built only out of the primitives we've already seen, and that's the race. What the race does is once any of its inputs have been resolved, whether in failure or success, then it simply resolves the output.
So these are OR gates and AND gates.
I'm suggesting that with the diagrams, but I didn't say that. But yes, these are basically OR gates and AND gates. the last time I gave this, which was the Vail IEEE Computer Elements Conference, it was asked, why are they pointing backward? And that's actually worth talking out. These promises are asymmetric. You know, one direction is very different from the other direction, but they're not simply unidirectional. There's one kind of information, messages, that propagates in
There's
one
requests
direction.
and responses, and they go in opposite directions.
That's right. That's right. The resolvedness signal propagates in the opposite direction from the messages. What I found was, as long as I drew my arrows with conventional triangular arrowheads at the arrowhead, no matter which direction, which side I put them on, as long as they looked like a conventional arrowhead, I could not explain the information flowing in the other direction. So that's why it's circles and triangles and other graphical clues here, but it's especially why on almost all my slides I do a consistent left to right is message flow and right to left is resolvedness flow.
The symbol for a race, isn't that a not symbol rather than no symbol?
Alan,
I thought an or symbol had curved
Yeah, the
sides
or has the curved and
and
the,
curved back going to a point.
yeah, the or has
Oh.
the curved and the and has the point.
This symbol is usually used for an op-amp. An
Yeah.
inverter is this symbol with an extra circle on the tip.
wow, so I got this very wrong. Okay, I will
Check the notation.
check the notation and fix that.
Get your circuits 101 book.
Yeah, my intention, of course, was race is or and all is and.
Yeah.
Okay.
The OR gate, all three sides are
I think it's the wrong symbol.
Okay. So, so an example of where this race is very useful is, for example, a timeout. If we do an eventual send of the foo message to Bob, if we race that with a promise that after 5,000 milliseconds will resolve to a broken promise, broken with timeout, what that means is that if something like 5 seconds goes by without Bob responding to the foo message, then answer P will still get resolved one way or the other. Okay. So now we can enhance our transaction coordinate. I'm sorry. Next, we can enhance our transaction coordinator pattern by racing the previous all with these. We give to the participants these emergency cords like you have on a train or a subway for stopping the vehicle, and we do that because it should not be up to the transaction coordinator when to time out based on
Yes.
non-response by the customers. It's really up to Alice and Bob whether whether they've decided they'd rather have their assets back rather than continue to wait for the
Yes.
transaction
You
to
can
move
always
forward.
take the offer off the table.
That's right. So, and the
What happens if one of the parties pulls the emergency cord at about the time that the transaction?
Oh, then there's a race.
yeah, then there's a race, and it's non-deterministic who wins the race, and that's fine.
Yeah, I agree. That's fine. I'm just thinking: are there any bugs here? Is it possible for the emergency cord to cause an inconsistent outcome?
That would
Well,
be
the fact that
How do we know that it won't?
because the decision only depends on the result of the race, and the phase 2 commit or abort action depends only on the decision.
there's a single decision being made, and that's the fact that there's a joint there, that both participants will behave the same way after that. They'll either get success or they'll get failure. You won't have one of them getting each.
Right.
Let me think. Hang on. I'm looking at the code for coordinate in general 2PC pattern transaction and stuff.
Yes.
And the race is outside the all.
That's correct.
It's possible for that race to resolve to one of the failures, even though the decision has succeeded.
No, not even though the decision has succeeded. It can only happen if all of the phase ones succeed. I mean, what you mean is, if all the phase ones succeed, the decision can still, it can still be a failure. If a failure wins the race, then the decision is still failure. So let's say that all four input conditions happen at the same time.
Yeah.
Well, then the all itself will be a success. I'm sorry, let's say.
Oh, I see. Yes, you're right.
Okay,
Yes,
good.
so I misread the code. Okay.
Okay.
Fine.
And what the fail only does is it ensures that pulling the cord can only contribute towards a decision to abort. It can't contribute towards a decision to commit. So here's the definition of fail only. I'm actually taking a shortcut here, which I didn't actually explain what when does when you only provided one argument, which is a propagates breakage. But in any case, so we just add the code, and so using fail only, we add the code that's not gray here, which is we surround the all with q.race, and we add the two fail onlys around the cord provided by Alice and Bob. And now we have a secure, unstuck escrow exchange agent. All the participants have the ability to terminate the transaction if they get impatient. So altogether here, sorry, what?
Two thoughts. You might call that cancel instead of cord. That might be a bit more immediately obvious. And you may need to mention, when you're talking about q.race, you may need to mention that promises are only resolved once and that subsequent calls to resolve are ignored.
Ah, yes, good, good. So next,
another suggestion: rather than using the one argument form of when here, you could just have a function that does nothing as the success argument.
so if it does nothing,
That would avoid having to introduce that.
no, unfortunately, if you say open curly, close curly as the success, in JavaScript, as you know but might have forgotten, that returns undefined. And then that will resolve the result of the when successfully to the value undefined.
Oh, I see. So you want an identity function as the first argument. Is that right?
For the first argument, I say
success returns success.
what I want to do is I want to ensure that if no matter how the cord resolves, that the result of fail only is either unresolved or a broken promise. It never resolves successfully. That's really the only constraint here, is that the result of the fail only can never resolve successfully.
Okay. So it's like returning a result of Q defer where the resolver is never called. The success function.
So that would be a perfectly adequate success function. This one is both simpler and actually a little bit more useful, because now the input to the fail only can validly be a promise for the exception to be thrown, and that's a perfectly fine way to cause failure.
Oh, I see. Yeah.
Okay.
Okay, so conclusion slide. So altogether, what you've seen here is 20 lines of code representing sort of the general concept of money bank
We're
stock.
missing a slide. You need to have a slide showing the 43 lines of code, even if it's a small font, just to show
Yes,
it.
that would be good.
You're right, very good. 16 lines of code to express,
Perhaps in 2 columns.
yeah.
Just one, just put it there in a small font. Nobody's going to read it.
And how it lays out, I suspect 2 fonts it'll actually be prettier, but how it lays out, we'll see. But I think you're right. 16 lines of code to express the two-phase commit that's insecure and also can get stuck under non-response, and then 5 lines to secure it with regard to conventional attacks, and 2 lines to make sure it doesn't get stuck. So that's 43 lines altogether. And the brevity here, I think, is a symptom of the fact that these are decent abstractions for doing the secure distributed programming.
There's another, this is a subdivision of the code that you've shown. There's
Yeah.
another one I would like to see, and that is you've abstracted two-phase commit. It'd be interesting to see all of that, not the driving of that object, but the implementation of the two-phase commit.
Just itself.
It would be interesting to see that abstracted away, or excuse me, isolated.
So really, I mean, that's,
That's it.
yeah, it's this slide and this slide.
Yeah, yeah,
General two-phase commit pattern
Yes.
transaction coordinator,
yes,
and general two-phase commit pattern participant.
yes.
Yeah, and that, yeah, I mean that just, I mean that's that was actually the thing that inspired turning this into a separate talk, is just realizing how beautiful two-phase commit by itself is when expressed with promises.
Before, two-phase commit was a pattern. Now it's a piece of code.
Yes. Okay.
And conveniently, 2 separate sections are about the same number of lines, so you can fit them into 2 columns side by side.
There you go. Yeah, the bank and the bank and the commit and the escrow agent. Very cool.
Okay.
Very cool. You've only been working
I
on
like this talk.
since 10 years
Good
before I
talk.
first met you.
Yeah.
If this were a course, I think it's a week's material.
Well, there's a lot of background here that are
Yes.
obviously
Mhm.
deleting.
Yeah. So twice now, I use this talk in a 20-minute time slot.
I can't imagine the audience getting much
Wow.
other than a magic show.
Well, I mean,
For the right audience, they could get it.
what they got, what they didn't follow the code in detail, but because I put so much emphasis on the diagrams, they sort of understood what the point of it was.
I think you can understand the claim in 20 minutes,
Yeah.
and then go away and study the code and have a chance of
So-
understanding it.
So but there's also something very significant here for general programming. We have talked about a turn being transaction. But there's this issue of how do you implement transactions across VACs?
Yes.
And this answers
Yes.
that question.
Yes.
So this is a general pattern for transactions across VACs
Yes.
Mhm.
is very important.
Yep.
And I don't think Stigler in particular is aware of this pattern.
He is now.
Okay.
He
So he was there.
He was there in Vail. Yeah.
All right. Well, I think it's lunchtime here.
Okay. Thank you.
Yes.
Okay. Bye.
Bye.
When I'm on a conference call, particularly, to just sit silently